Statistics Lesson 3-3, Measures of Relative Standing and Boxplot. The objectives to develop the ability to compute a z-score and use the result to determine whether a given value x is significantly low or significantly high. Identify percentile values and quartile values from a set of data. Develop the ability to construct a box plot from a set of data. Measures of relative standing. Numbers showing the location of data values relative to the other values within the same data set. A z-score is the number of standard deviations that a given value x is above or below the mean. It's calculated z equals x minus x bar divided by s, or z equals x minus mu divided by sigma, mu being the standard deviation. Let's see, x bar is the sample standard or sample mean. S is the sample standard deviation. Okay. And then mu, pronounced mu, is the population mean. And sigma is the population standard deviation. All right. Round off rule. Round to 2 decimal places, the sample standard deviation and the population mean, and the sample mean and the population standard deviation. Round to 2 decimal places. Properties of z-scores. A z-score is the number of standard deviations that a given value x is above or below the mean. A z-score is expressed as numbers with no units of measurements. A data value is significantly low if its z-score is less than or equal to -2, or the value is significantly high if its z-score is greater than or equal to 2. If an individual data value is less than the mean, its corresponding z-score is a negative number. All right, so here's an example here. Let's compare these two. Which of the following 2 data values is more extreme relative to the data set from which it came? The first one, 400-gram weight of a newborn baby. Among 400 weights, the sample mean x bar equals 3,125 with a sample standard deviation of 693.4 grams. And we're going to compare it to the temperature of an adult among 106 adults with the sample mean 98.2 degrees Fahrenheit and a sample standard deviation of 0.62 degrees Fahrenheit. So z, the first one, maybe I'll just do it right here, z equals, and we're going to have 4,000, that's the x, minus the x bar, 3,125, divided by 693.4. All right, so let's try that in our calculator. Let's go to calculator, control, divide, 4,000 minus 3152 693.4. Check my equation there. 4,000. All right. And let's press enter. And we get 1.22. So we have a z-score of 1.22. Now let's check the body temperature. We're going to have 99 minus 98.2 divided by 0.62. And let's see what that is. Now, what do you think? Which one's further off? Control, divide, 99 minus, which one's further from the mean? 98.2 over, let's see, 0.62. And we get 1.29. 1.29. All right, so what can we say here? We can say the 4,000 gram birth weight is 1.22 standard deviations above the mean. And the 99 degrees Fahrenheit body temperature is 1.29 standard deviations above the mean. Because the body temperature is further above the mean, it is a more extreme value. So this one is the more extreme value. It's further from the standard deviation. All right, that's not too hard. The lowest platelet count in data set 1 body data is 75. The platelet count is measured in 1,000 mean liters or something like that. Is that value significantly low? Based on the platelet count from the data set 1, assume that the platelet counts has a mean of 239.4 and a standard deviation of 64.2. So let's see what we got here. Z equals, and then we've got 75 minus 239.4 divided by 64.2. All right. So let's go to our calculator, control, divide, and we have 75 minus 239.4 over 64.2. And we got negative 2.56 equals negative 2.56. So what does this say? The platelet count of 75 converts to a z-score of z equals negative 2.56, which is less than negative 2. And what, you know, when you're first starting to do this, maybe what you need to do is draw a line here, okay? So you have the mean here, okay? And we're working with x bar, so you got x bar. You got one standard deviation, you got two standard deviations, 1, 2, and then negative 1, negative 2. And then let's see where this negative 2.56 is. Okay, it's over here somewhere. Okay, so we're going to say that it is significantly low. All right, later on you're going to learn that 95% of the data is between these two right here. Okay, all right, in a normal plot. Percentiles are a measure of location denoted P sub 1, P sub 2, and so on to P sub 99, which divide a set of data into 100 groups with about 1% of the values in each group. The formula is percentile value of X equals the number of values less than X divided by the total number of values times 100. Okay, now that may sound a little bit vague right now. So let's go to our calculator. And what do we got here? We're looking for the Verizon data. And I went ahead and put it in. So let's see, doc. And then when I put these in your calculator, this is how you find them. Open doc. And then Verizon. Oh, good, it's in there. Verizon data. And then, no, I don't want to save the end. All right, so there's my data. Okay. So I want to find the percentile. Let's see, let's go back. I want to find 11.8 megabytes per second. Find the percentile for that. Okay. Now, if you look, I have 50 data. That's not. And then we can just kind of go down and we see we got 50 data. Okay, so let's go back to our equation. And what goes total number of values, 50. And then we're going to say times 100. And so our percentile, all right, let's see, 11.8. Now, here's the thing. These are not in order. They've not been sorted. So I'm going to click here, and I'm going to say Menu, 1, and Sort. And I want to sort ascending from smallest to largest. And there we go. All right. Now, we just scroll down here until we find 11.8. Oh, there it is. All right. So how many values are above 11.8? It was 20. So I got 20. All right. So 2/5 times 100. Well, these cancel. And that's going to give me 40. Okay. So the percentile of 11.8 megabytes is 40. Okay. It may be written something like this: percentile 40 equals 11.8 megabytes per second. Okay. Now, what if I wanted to find P25? What if I wanted to find P sub 25? I wanted to find the 25th percentile of P. So to do that, I would need, let's see here, 25, and out of 100 times 50, what is that going to give me? 25, that's 1/4, 1/4, 1/4 of, let's see, let's just do the calculator. And we'll go get the scratch pad there. And we had control divide 25 over 100 times, was it 50? All right. I hate when it does that. Control divide 12.5. Okay, I don't have a 12.5. Okay, so I'm going to have to go up to the next number, 13. So let's find where 13 is. 13 is 7.9. Okay, so here we got P sub 25 is 7.9 megabytes per second, and that was supposed to be a capital M. Megabytes per second. All right, that's not too difficult. Well, why don't we find the 40th percentile while we're at it? P sub 40 equals, and then we're going to say 40 over 100 equal, or times 50, times 50. So let's try that. And I'm just going to go up there and grab that. And I'm going to take out 25. And I'm going to put 40. Okay, so that one gave me 20. That one gave me 20. Okay, so I'm going to, let's see, here we go. And let's find number 20. Okay, 20 is 11.6. And 21 is, so I want above 11.6, okay? And the next number is 11.8, and halfway between those would be 11.7. So, okay, equals, and that was 20, okay? So remember, 20 should be below it, and we got P sub 40 is, what did I say that was? 11.7. 11.7 megabytes per second. It's halfway in between 20 and 21, right? All right. Well, 20 is below it, but it's not quite 21 either. Quartiles are measures of location that denoted Q sub 1, Q sub 2, and Q sub 3, which divide a set of data into 4 groups with about 25% of the values in each group. So Q sub 1, or P25, it is called the first quartile, and it's the same value as P sub 25. It separates the bottom 25% of the sorted values from the top 75%. Okay, so it separates bottom 25% from top 75%. Okay, and I guess another way to say it is at least 25% of the sorted values are less than or equal to Q sub 1, and at least 75% of the values are greater than or equal to Q sub 1. Q2 is called the second quartile. The second quartile. And it separates the bottom 50% of the sorted values from the top 50%. So the bottom 50% from the top 50%. And in Q3, sometimes called the third quartile, separates the bottom 75% from the top 25%. Okay? Now we're going to work with these in a little bit, but you can use the procedure that we just used to find P sub 25 and P sub, or Q sub 1, Q sub 2, and Q sub 3. The interquartile range is Q sub 3 minus Q sub 1. Okay, and that's another statistic that is sometimes used. The semi-quartile range is Q sub 3 minus Q sub 1 divided by 2. The mid-quartile range is Q sub 3 plus Q sub 1 divided by 2. And the 10 to 90 percentile range is P sub 90 minus P sub 10. Now, I want to show you something while we're here. We went and sorted all that data, okay? We went and sorted all that data. Now, it'll also help you find Q sub 1 and those real quick. Try menu 4 1, 1, and number list is 1, and we're going to call it data. Okay, and there we go. Not only did it give you the mean and the standard deviation, but if you scroll on down, you see it gives you the minimum value, the Q1, the Q2, and the Q3, and the max value, which that brings up the next thing. Okay, that brings up the next thing. The 5-number summary. Okay, the 5-number summary. So let's see, what do we got? The minimum. Let's go to a calculator. The minimum is 0.8. 0.8. Q sub 1 is 7.9. 7.9. Q sub 2, same as the median, is 13.9. 13.9. Q sub 3 is 21.5. 21.5. And the maximum is 77.8. 77.8. Okay? And we use those to graph something called a box plot. And a box plot, or sometimes called a box and whisker diagram, is a graph of a data set that consists of a line extending from the minimum value to the maximum value, and a box with lines drawn at Q sub 1, Q sub 2, and Q sub 3. Well, let's try one. Let's try one. So I got my stuff right there. Let me kind of get us some white space here. Got us some white space. And then I need to draw a line. And let's see, we got us a nice line right here. Okay, this is your line. And let's see here, what do we got? We've got 0. I'm going to do it black, so I'm consistent. 0. And let's see, my highest number is 77.8, so I'm going to put an 80 right here. And maybe halfway in between, put a 40. And let's see, 10, 20, 30, and then 50, 60. That didn't quite work out. 70, and I'll move 80 over here. I'll move 80, make it kind of symmetric. Okay, I like for it to be a little symmetric. 10, 20, 30, 50, 60, 70. All right, so what do we got? We got our minimum is 0.8, and we're going to say, let's see here. Let's use that. 0.8, we're going to say that's right there. And that's our minimum, and our maximum is 77.8, and we'll say that's about right in there. Okay? Now we got Q1 is 7.9, and we'll say that is maybe like right in here. And then Q2 is 13.9, so we'll say maybe it's right there. And then Q3 is 21.5, so that's just past that. Now let's just let's draw some box. Yeah, let's see here. Let's draw some box. See if I can get a straight line there, and maybe another one right here. Okay, there's our box, and then we connect the two sides. And we have our box and whisker plot. Okay, not too shabby. Now, what's really neat about this? Doesn't it just kind of show you the skewedness right there? This data set is skewed right. Okay, it is skewed right. Which that also brings up something else. What does it being skewed right? Doesn't that kind of like drag the mean to the right? Anyway, all kind. We'll talk about that stuff more later. So there's your box and whisker plot. A box plot can often be used to identify skewness, which I just showed you. When analyzing data, always identify outliers and consider their effects, which can be substantial. And let's see, in a modified box plot, a data value is an outlier if it is above Q3 by an amount greater than 1.5. Okay, so Q3 plus 1.5 IQR, or below Q1 by, say, Q sub 1 plus 1.5 times the IQR. So let's calculate those. What was it? Q3 was 21.5. So we got 21.5 plus 1.5 times, and then 21.5 minus 7.9. 21.5 minus 7.9. And let's put that in our calculator. So we had 21.5 plus 1.5 times, open parentheses, and what do we have? 21.5 minus 7.9. 0.5 minus 7.9. Enter. So that's 41.9. 41.9. And let's see here. Q1, and I put by an amount greater than, okay. So that's going to be actually minus, I should have put a minus in there. So we're going to have, was it 0.8 minus 1.5 times 21.5 minus 7.9. Okay. That was Q1, wasn't it? Let's see what, that was the minimum. That was the minimum, I can't remember. Q1 is 7.9. So we got 7.9. Okay, so let's try that. We got 7.9. And let's go in here and we'll 7.9 minus, and that, and see what we got. Negative 12.5. Negative 12.5. Well, let's go back. Did we have numbers above 41.9? I'm sure we did. Sometimes you have something called a modified box plot, and I didn't mean to do that. A modified box plot. So let's put that up. Let's go back to our calculator. We wouldn't put all this stuff in. We can also draw a box plot on this, and the Inspire actually does the modified box plot for you. So you press on, and in the graph, and we call this data. To make it into a box plot, menu, 1 for plot type, 2 for box plot, and it does it for you. And remember, we calculated the IQR, and the IQR was anything above 40, or an outlier was anything above 41.9. Well, look, here you got a 43, a 55.6, 71.3, and 77.8. Those four data are dragging your mean to the right. Okay? They are dragging your mean to the right, which that'll become a lot more important in the later chapters. All right. Y'all have a great evening. I appreciate you, and we will see you in class tomorrow.